we've already learned that cellular respiration can be broken down into roughly 3 phases. Cellular respiration broke down into 3 phases. The first is glycolysis. Glycolysis, which literally means the breaking down of glucose. Breaking down of glucose. And then this can occur with or without oxygen. If we don't have oxygen, then we go over to fermentation. We'll talk about that in the future. Go over to fermentation. In humans, it produces lactic acid. In other types of organisms, it might produce alcohol or ethanol. But if we have oxygen, and for the most part, we're going to assume that we can proceed forward with oxygen. If there is oxygen, then we could proceed forward to the Krebs cycle. Krebs cycle, sometimes called the citric acid cycle because it deals with citric acid, the same thing that's in orange juice or lemons. And then from there, we proceed to the electron transport chain. Electron transport chain. And we learned in the first overview video of cellular respiration that this is where the bulk of the ATP is actually produced, although it uses raw materials that came out of these phases up here. Now, what I want to do in this video is just focus on glycolysis. Just focus on glycolysis. And this is kind of a, it's sometimes a challenging task because you can really get stuck in the weeds. And I'll show you the weeds in a little bit in the actual mechanism, and it can be very daunting. But what I want to do is simplify it for you so you can kind of have the big takeaways, and then we can appreciate, and then maybe when we look at the weeds of glycolysis, we can make a little bit more sense of it. So glycolysis, or really cellular respiration, it starts off with glucose. It starts off with glucose, and glucose, we know its formula. It's C6H12O6, and I could draw its whole structure. It would take a little time, but I'm just going to focus on the carbon backbone. So we could, it is a ring, or it can be a ring, but I'm just going to draw it as 6 carbons in a row. Now, there's 2 kind of important phases of glycolysis that are good to know. One I call the investment phase. And the investment stage phase actually uses 2 ATPs. So it actually uses 2 ATPs. So, the whole purpose of cellular respiration was to generate ATPs, but right from the get-go, I actually have to use 2 ATPs. But I use 2 ATPs, and I'm going to essentially break up the glucose into 2 3-carbon compounds right here that actually also have a phosphate group on them. The phosphate groups are coming from those ATPs. They also have a phosphate group on them. This is often called, well, there's a lot of names for it. Sometimes called P-gal. You really don't have to know this. Or glyceraldehyde, really challenging my spelling skills right here. That's not that important to know. All you have to know is in this first phase, you use 2 ATPs. That's why I call it the investment phase. If we use a business analogy, investment phase. And then each of these 2 P-gal molecules can then go into the payoff phase. So in the payoff phase, each of these P-gals turn into pyruvate, which is another 3-carbon, but it's reconfigured. But the process of it going to pyruvate, and let me write pyruvate in blue, because this is something that's, at least it's good to know the word. And I'll show you its structure in a second. Pyruvate, sometimes it's called pyruvic acid. Same thing, pyruvic acid. And that's essentially the end product of glycolysis. So you start off with glucose. In the investment phase, you end up in this phosphoglyceraldehyde, which essentially you broke up your glucose and you put a phosphate on either end of it. And then those each independently go through the payoff phase. So you end up with 2 molecules of pyruvate for every molecule of glucose you started off with. Now you're saying, hey, so it was a payoff phase. What was our payoff? Well, our payoff we got from this, let me write this down as a payoff phase. This is our payoff phase. And I apologize for the white background. I did it because the mechanism I'm showing you, I copy and pasted it from Wikipedia, and they had a white background, so I just ran with the white background for this video. But I personally at least like the black background a lot better. But this is the payoff phase right here. And so when we go from the phosphoglyceraldehyde to the pyruvate or the pyruvic acid, we produce two things, or I guess we could say we could produce three things. We produce each of these p-gals to pyruvates produce two ATPs. So I'm going to produce two ATPs there. I'm going to produce two ATPs there. And then they each produce an NADH. NADH. May I do it in a darker color? NADH. NADH. And of course, they're not producing, they're not producing the whole molecule in a vacuum. Essentially, what they're doing is they're starting with the raw material of an NAD+. So they start off with an NAD+, and they essentially reduce it by adding a hydrogen. Remember, we learned a couple of videos ago that you can view reduction as a gain in hydrogen. So the NAD gets reduced to NADH, and then later on, these NADHs are used in the electron transport chain to actually produce ATPs. So the big takeaway here, if I were to kind of write the reaction that we get for glycolysis, is that you start off with glucose. And you need some NAD+. And actually, for every mole of glucose, you're going to need two NAD+. You're going to need two ATPs. So I'm just writing all the ingredients that we need to start off with. And then you're going to need, these guys are going to be ADPs before we turn them to ADPs. So I'll write plus 4 ADPs. And then after performing glycolysis, and let me write it here. Let me write also that was an ADPs. Let me just rewrite that part right there. 4 ADPs, and then you maybe need 2 phosphate groups because we're going to need 4 phosphate groups. Plus 4, I'll just call them. Sometimes they're written like that, but maybe I'll write it like this: 4 phosphate groups. I'll do 4 phosphate groups like that, and then once you perform glycolysis, you have 2 pyruvates. You have 2 NADHs. The NAD has been reduced. It gained a hydrogen. RIG, oil rig. Reduction is gain in electron, but in the biological sense, we think of gaining the hydrogen because hydrogen is very non-electronegative, so you're hogging its electrons. You gained its electrons. So 2 NADHs, and then plus these 2 ATPs get used in the investment phase. That's why I kind of wrote them a little separately. So these 2 get used. So then you're left with 2 ADPs. And then these guys essentially get turned into ATPs. So plus 4 ATPs. I guess we didn't need 4. We only needed a net of 2 phosphate groups because 2 jump off of here, and then we need a total of 2 more to get 4 jumping on there. But the big picture is you start with glucose, you end up with 2 pyruvates, you use up 2 ATPs, you get 4 ATPs, so you have a net of 2 ATPs formed. Let me write that very big. Net, what you get out of glycolysis is 2 ATPs, you get 2 NADHs that can each later be used in the electron transport chain to produce 3 ATPs, but you get 2 NADHs and you get 2 pyruvates, which are going to be re-engineered into acetyl-CoAs that are going to be the raw materials for the Krebs cycle. But these are the outputs. These right here are the outputs of glycolysis. So now that we have that big picture, let's actually look at the mechanism, because this is a little bit more daunting when you see it here. But we'll see the same themes that I just talked about. We're starting with the glucose right there. It is a 6-chain. It's in a circle. It's in a ring. 1, 2, 3, 4, 5, 6 carbons. I could write it like that, just to make it a huge oversimplification. Goes through a few steps. I use an ATP here, so that's, let me do that in a color. We do it in orange whenever I use an ATP. I use 1 ATP there. I use 1 ATP there. And just like I told you, they have a slightly different name for it, but this is the phosphoglyceraldehyde right here. They call it glyceraldehyde 3-phosphate. It's the exact same molecule. But as you can see, just when I drew it very roughly before, you've got 1, 2, 3 carbons there. 1, 2, 3 carbons there, and it also has a phosphate group on it. The phosphate group's actually attached to the oxygen, but for simplification, I draw the phosphate group just like that. And I showed that right here. This was the phosphoglyceraldehyde right here. This is the actual structure up here, but I think sometimes when you look at the structure, it's easy to miss the big picture. And there are two of these. They kind of say that you can go back and forth with this other kind of isomer of this. But the important thing is that you have two of these compounds that are now 3 carbon compounds. Glucose has been split, and now we're ready to enter the payoff phase. And remember, you have two of these compounds right here. That's why when they drew this mechanism, they wrote times 2 right there, because the glucose has been split into 2 of these molecules. So each of the molecules are now going to do this right here. And for each of the glyceraldehyde 3-phosphates, or PGALs, or phosphoglyceraldehydes, we can look at the mechanism. And say, okay, look here. There's going to be an ADP turning into an ATP there. So this is plus 1 ATP. And then we see it again happening here on our way to pyruvate. Right there. Then we have another plus 1 ATP. So for each of the PGALs, or the phosphoglyceraldehydes that were produced, we're producing 2 ATPs in the payoff phase. Now there were 2 of these, so total for 1 glucose, we're going to produce 4 ATPs in the payoff phase. So in the payoff phase, 4 ATPs. In the investment phase, we used 2 ATPs. So total net ATPs directly generated from glycolysis is 2 ATPs. Right? 4 gross produced, but we had to invest 2 in the investment phase. And then the NADHs, we see right here. For each phosphoglyceraldehyde, or glyceraldehyde 3-phosphates, or PGALs, or whatever you want to call them, at this stage right here, you see that we are reducing NAD plus to NADH. So this happens once for each of these compounds, and obviously there are 2 of these. Glucose got split into 2 of these guys, so 2 NADHs. 2 NADHs are going to be produced, and later these are going to be used in the electron transport chain to actually each produce 3 ATPs. And then finally, when everything is said and done, we're left with the pyruvates. And it's nice that at least they made it nice and big. We can take a look at what a pyruvate looks like. And just as promised, we can look at all the oxygen bonds and all of that. But it is a 3-carbon structure. It has a 3-carbon backbone. So the end result is that the glucose got split in half. It got oxidized. Some of the hydrogens got stripped off of it. As you can see, there's only 3 hydrogens here. We started off with 12 hydrogens in glucose, and now it has carbon is bonding more strongly with oxygen, so it's essentially having its electrons stolen by the oxygens, or hogged by the oxygens. So carbon has gotten oxidized in this process. There's going to be more oxidation left to do, and in the process, we were able to generate 2 net ATPs, and 2 NADHs that can later be used to produce ATPs. Anyway, hopefully you found that helpful.
Thank you for watching this video. Don't forget to like the video.